Hi, everybody. First, I want to just say thank you to the organizers for putting together such a fun event. I do a lot of events. I think this is the most fun I've had at an event in years. So thank you. This is great. And I also want to thank the audience and all the participants here because I've had a chance to talk to a lot of people, and it reminds me of that saying that the smartest person in the room is the room itself. And I really believe that. So I think collectively together, we just have a lot of brain power, and there's a lot we can do together. So I'm looking forward to continuing to connect to everybody. The next few minutes, we're going to talk about graphs and why they're so good for predictions. We're going to talk a little bit about connected features, as well as link prediction and a little workflow in Neo4j and Spark together. This book just came out on the 15th of this month. You can get a free copy at this URL. A lot of what I'm going to talk about is covered in this book, or covered in more detail, and I'll show this again at the end in case you miss it. So, thinking about trying to predict things, I would like to think about voting and smoking. Very different things. If we want to predict somebody might be a smoker, or whether they're going to vote in the future, there's actually something in common that can help us make these predictions. I don't know if anybody might guess what that is. It's actually relationships. So those two examples are from a book where they did a lot of, based on research. This book is really good for research examples. And they actually looked at how you can use relationships to predict things about people's behavior and how strong. So for example, in that voting sample, they actually looked at not just whether your friends vote or whether your spouse votes or whether your coworker votes, but they actually found that what's even more predictive than that was whether your friends' friends vote. So people you don't know can be predictive of whether you're going to vote or not. So relationships are very predictive, and we should be using those in our machine learning models because they help us improve our accuracy. Because I love books, I'm going to show you a couple other books that I really like. The Connected book is really great for basic research. There's a lot of information in there. There's another one called Friend of a Friend, written by a great man, David Burkus, about extending your career through your friend networks. He's got a lot of useful tips there. And then Barabashi also recently put out another book. He's put out many network science books. This one's more about using your connections for your career. So I love book recommendations, so I'm going to give you a few of those. But we know relationships are sometimes the strongest predictors of behavior. Graphs are a mathematical representation of networks, of relationships. We call entities nodes in the terminology that we use. We call relationships relationships. Makes that easier. But we see them everywhere. And there's a long history of studying networks through graph mathematics and graph theory. You can think of them as something you might see on a transportation network, but there are also brain networks. There's the networks in banking and finance. There's customer graphs and networks. So all of the information around us is, at least today, is highly interactive and highly connected as well. And we know that these connections are very predictive. Yep, there we go. And so it's not surprising that trying to use those connections is increasing quite a bit. So the green line, you probably can't read the chart, the top green line actually shows the trend in popularity of graph databases compared to all other database types. Relational databases down here at the bottom just because everybody's already using them, so they're not really increasing as much. But you can just see since 2013, the interest in using graph-based platforms has increased dramatically. And what do people use them for? How are they using this connected data? In data science, there's quite a bit of use cases. It really kind of scales horizontally. Financial crimes and anomaly detection, anti-money laundering, fraud, really a typical use case. Drug discovery, drug repurposing. So how do we actually figure out how to repurpose things for other uses? Recommendations in retail, another one. Cybersecurity, probably not surprising. So lots of different types of use cases for this highly connected data. I was just talking to somebody about churn prediction a few minutes ago, and actually predicting not just who's going to churn, but are they going to pull other people? Are we going to have a cascading effect of churn? And we can see that if we're looking at the connections between data. So the idea in regards to using connections in data is to look at the information that you already have. So a lot of data science methods right now actually ignore the structure of the data itself. It doesn't look at the topology, or you're force fitting it into tables and doing your possibly some joins and then adding it into your pipeline. And what we would really like to see is people use this highly predictive features, all these elements in your data, use what you already have and bring it into your pipeline. Don't throw your pipeline out. Don't totally replace what you might be doing with your maybe flat data, but just bring in that relationship and add those predictive elements. Now, the easiest way to do that is actually using what we call connected features. And connected features are really just features that have some graphy element, that are using the connections within your data. And that could be something as simple as, how many relationships does this person have? How many relationships that 4 hops out might be fraud related? Like how many fraudsters in your network? 5 hops out. Do a score, bring that in. So that's really just kind of looking at what might already be in the data and then making it into a metric and a connected feature for your machine learning. Now, there's a couple different ways you can get this information out of your data. You might do a simple query. You might say, hey, I want to know, in the fraudster example, I want to know how many fraudsters are 3 hops out from somebody. I can do a quick query, I can get that information back, and I can do a scoring. Or maybe I want something more global. Maybe I want to understand more about the overall topology of the network, and I'm looking for extremely tight communities, and then I want to score the people in those communities. Those more global computational analysis are where the graph algorithms come into play to kind of pull out the structure of the data and find interesting elements. Now, when we're talking about connected features, there's 3 different types of ways you can use connected features in your machine learning. The first one is feature extraction. Like, how do I change the shape of the data that I already have so I can use it in my pipeline? Some of the people were talking about different ways to do that earlier. One way might be just, quite easily, as I said, trying to do a query and pulling some information out. Maybe I'm just trying to extract a subset. So in this case, I just have a graph that I'm extracting a community that, let's say they're strongly connected because they actually have a relationship following the arrows, so following the direction of the relationships where everybody can reach everybody else. I can do that, score it, put it into my machine model and go, as opposed to having to do hand cleansing and iterating on that. It allows me to more quickly move to my training. The next area is the area that I think is probably the most exciting, is feature engineering. We talked about that earlier today. And that's basically, you're trying to create new features, with the data you already have. When we're talking about graph, we're trying to create new features based on that connected information. I don't know if you guys can see this. This is actually Game of Thrones. We love to play with this. We actually have Game of Thrones data sets in a graph if you want to play with it. On our site. But you might be trying to extract features like, who has more influence? I want the top 5 nodes with the most influence over relationships or the flow of information in my network. I'm going to score them as highly influential, and then I'm going to do some machine learning on those scores. It might be how connected, how many triangles, how tight are their communities. It might be something just simple of, basic categorization. What are these groups categorized as, and then score that and bring that into the machine learning workflow. The third way that you can use connected features in your machine learning is feature selection. So if you think about it, feature selection helps us bring forward the most influential elements in our data and get the non-influential elements out, or the non-influential features. And somebody talked about that earlier today, where if you have too many features, you're overfitting your data. And we can do this, of course, with a domain expert that says, hey, I know these items are more influential, we're gonna use those, but you can also use graph algorithms to do that. So there's a couple really good papers about using PageRank. I'm gonna assume most people here know what PageRank is. Have you used it? Some, maybe not, but it's like most people. But basically, PageRank was made famous by Google and invented by Larry Page to help us return more credible sources of web pages when we're doing our searches. But what it actually finds is it finds a transitive influence. It finds not direct influence, but influence related to other influence that nodes or pages may have given somebody. So by the inlinks, you get more influential score. What's interesting with looking at features, we can do this with features, and we can rank features against each other and say, these features have a higher page rank, the rest of them are noisy, we're going to eliminate some of the rest of those. So that can basically help reduce our overfitting. And I wanted to kind of dive a little bit into link prediction in particular in this scenario, because predicting a link is something we see a lot of requests for. And the idea of predicting a link is that you're trying to infer an interaction in the future or try to find missing data. So the fact actually is there, it's just not in our data. There's a really interesting paper on unobserved facts with criminal networks, where they're actually trying to predict links or finding missing links, if you will, between certain criminal organizations and then targeting those links. So there's some really interesting papers. But the idea is that you start off with some kind of a graph. You're trying to predict based on the topology that there may be a link in the future, and you just keep iterating on that as you get more information. There's a really cool example that I want to share with you. If there's anybody out there that's in biotech, and I talked to somebody who was a computational biologist earlier today, you really have to check out this website. It's called het.io. They have decades of biomedical information in a knowledge graph, and they're predicting new uses for drugs, so drug repurposing, based on the graph structure and using link prediction to estimate the potential of drugs reuse to other diseases. This is another screenshot. They actually have a browser, so you can go online and play with different diseases and genomes and drugs and look at what potential new links there might be. This example here, they're looking at multiple sclerosis, and they're looking at different genes and interactions involved in that. And this IRF1 does not have a direct link to multiple sclerosis, but you can see that it has links through other hops. So you're looking at secondary and tertiary and third level interactions. With storing something as a graph lets you traverse those paths much quicker. And they're also using some probabilistic methods to look at potential links as well. Now, the methods for link prediction that we help our customers with, usually two different methods. One is just basic algorithms. And so they basically are looking at running your typical algorithms that are kind of involved with link prediction. There's a category called link prediction. We'll talk about that. But there's also similarity algorithms. Which nodes in my network are most similar based on attributes, whatever those attributes might be like, and a community detection. How is my graph partitioned or grouped together? And basically what you can do there is you can set a threshold value. If it's above the threshold, you predict a link. If it's not, you predict there's no link. So that's one method. The other method, which I think is probably more interesting to this audience, is basically taking those measures and then feeding it into some kind of a machine learning model and making your prediction based on that. And I have an example of that, trying to predict collaboration between two parties. What we did is we actually looked at whether someone was going to collaborate based on a citation network. So we use that as a heuristic for collaboration. And we use this citation network data set. You can find it if you just search for ArtNet Miner. comes up pretty quickly. The paper that it's based on, it has a lot of data. We just used a subset of that. We looked at that to do a co-authorship graph. We created that in Neo4j, also used that to generate some of our features, and then used Spark and MLlib to actually train our model. So the process we went through, and this kind of workflow is probably similar even if we were to change out the product names of what you would do. So, basically, if you're going to try to do a link prediction workflow or any kind of actually machine learning workflow, at some point you're going to extract the data and get it in the format that you want. You're going to do some, in our case, we created a co-authorship graph, but you're going to create a data set with the points that you're trying to estimate. Then, of course, you go through the classic explore, clean, and modify, which is a lot of fun, but you can identify different areas that may be sparse in your network. It's at this point that you do your feature engineering. We use Neo4j to generate our connected features. Then you would go to preparing for machine learning itself. That's where you do your test train split, and you might have to do resampling. We actually had to downsample considerably because, as you can imagine, if you think about all the nodes in a graph, you're more likely to be not have collaboration than to have collaboration, so we had way too many negative samples to start with. Then, of course, you do your training, and I wish it was just a complete, little graphic snafu at the top, but I wish it was a complete left to right, but as most of you know, you're kind of doing your iteration. You play with something, it's not quite what you're looking for, you develop more features, and you kind of cycle through. And of course, you evaluate your results, and if we were trying to productize, we would productize at some point when we were happy, but we weren't doing that in this scenario. This is just for our own research. A few examples of the graph algorithms that we use for our feature engineering, and I say just a few because we actually did a lot of iterations and played a lot with this, but we used a lot of link prediction, and that link prediction algorithms tend to look at the topology, and based on the closeness, they say the closeness of two nodes, estimate whether structurally they would likely connect. One that was very predictive was preferential attachment, and that's kind of a network science term as well. And the idea is a node with a lot of connections is more likely to connect to another node than one without. And you can think of that as the classic the rich get richer phenomenon. If you have a large surface area, if your network is very large, you're more likely to bump into another node than somebody with a small surface area. So that one was pretty telling. The other one that really worked well for us in the citation was common neighbors. And that measures the number of possible triangles in somebody's network. And you can think of that as two strangers that have a lot of common friends are likely to be introduced to each other. So two coworkers or collaborators that have, or two research authors who haven't worked together but have a lot of co-authors in common, at some point they're going to be introduced. So that one, that was pretty predictive for us. Also, community detection. So just understanding a little bit about the community around a network. Triangle counting and clustering coefficient. I was surprised actually at how predictive this was because when you do general graph analysis, this isn't very sexy. It just counts, like for you, how many, there's two triangles in you, at least on the one side, or actually on both of them, and then the clustering coefficient is the likelihood that their neighbors are already to be connected as well. But when you use it in the machine learning, that actually is more predictive of whether people will collaborate in the future than I thought it would be. We also use several different community detection algorithms. We use label propagation, which I actually really like that algorithm. Louvain modularity as well, if any of you have played with that, identifies communities and hierarchies. So you can identify sub-communities and sub-communities and sub-communities. Looking at an intermediate community worked well for us. But there's a lot of different graph algorithms you can use. It's a matter of playing with your data and thinking about what might be predictive and then choosing an algorithm that might fit. But community detection seems very predictive overall, how things are clustered together. Link production, as you might expect, and then the similarity metrics as well, which I'm not covering today, are also something that are very commonly used. So I'm guessing that I'm starting to run short on time, maybe? Maybe not? No, oh, okay. It was just a phone. Okay, great. Fantastic, I have more time. So we used a random forest binary classifier to basically say, is there a link, or basically the classification was link or no link. And when we were training our model, this is just one decision tree. And basically we basically set our different thresholds. At each step, you decide, is it true or is it false, and you go on to the next step, and kind of then bring all of the decisions trees together to make your decision. Now, I don't know if you guys have had this happen to you, but on the first route, we got really good accuracy. We didn't do any tuning, it looked great, and if you get on your first round of training your model, I would say above 90% accuracy, and you haven't done any tuning, you probably have data leakage. And so with data leakage, what that means is that you have information in both your test and your trained data that represents the same information. In other words, you're cheating. And interesting thing about graph data, because graphs are all about connections and they're highly connected, data leakage is something you have to be really careful about. When we did this at first, we just did random splits, which is really typical. You're just going to randomly split and move. With graph data, that can be very, that lets you cheat, because we do have these connections that are predictive to other items. What we recommend people do is to do a split by time. So we went back after we got really 99% accuracy in just the first run. We went back and did a train test split by year. So everything before a certain year was our training, and then everything after a certain year was our test. As far as how we measured, we used your classic measures, accuracy, precision, recall, false positive, so I'm not going to go through all this. I always have to go back and try to remember which measures were which. But the two that we're going to take a look at, and you probably see the most, are your true positive rate and your false positive rates, and then of course mapped to your ROC curve as well. I will say the one thing that I always try to think about is that although it'd be nice to have all these scores, as high as possible, you also want to think about what your end user needs, because certain things are more sensitive to false positives, certain things are more sensitive to false negatives. False positives, an interesting story is that anybody doing kind of a financial crimes, in particular transaction fraud, so you're trying to order something online and there's a potential for transaction fraud, you would think you want as many positives as well as you could, but they actually let positives run through. So they're very sensitive to false positives, because chasing small amounts of fraud is actually more expensive than letting minor fraud go through, because they have to have an analyst go chase down every single item. And so you might have a client that is actually sensitive to one of these measures. So, tweaking the measures, it's not always one item or another that you might need. As far as our results, I'm going to show you our first model and then our last model, and not go through each one of them. But you can see your accuracy, precision, recall. We're at like 0.86 on this. That's really not that great. Each model down here that we're going to show you is made up of multiple related features. So they're not just one features, they're a different model, or they're multiple features together. This is actually showing here at the top a really problematic false positives. So we've got false positive rate here at the bottom, true positive right there on the y-axis. And in order for us to get correct true positive results at about 80%, I'm already almost in a 20% of false positives. So this is actually not very good at all. It kind of looks like it takes up a big area, but it's actually pretty poor results. Through many iterations and many learnings, we actually added in multiple different models and bringing them together, we found that our community detection was very telling here. So that was very helpful, and we were able to go from an accuracy of 0.86 to 0.99 and still have a good false positive rate as well. So our recall was up there up to 95, which you can see at the beginning was only 0.75, and that's where that 20% of false positives came in. So we multiple iterations trying to learn what worked for our model to try to finally tweak and get some good results. The other thing that I would say about using a method like this is you want to look at feature influence. So here we have the different features, not the models at this point, but we're looking at different features and looking at what is more influential. This is a result of the Spark random forest algorithm actually kind of averaging out what would be more influential of the features you're looking at. If I were doing this again, I might also play with PageRank, as I said, to kind of look at the influence and see what different results I would get. But maybe I would reduce these. Maybe these are features I don't want to look at. Or maybe if I reduce this feature for some reason, I might get different results on the other influence. So it's kind of interesting to kind of look at the different things that may be influential. Triangles are actually pretty influential. Being in the same partition, so the same community, is actually pretty influential on that as well. So a lot of different things you can do to just kind of compare and tweak your features. But you definitely want to take a look at that and not just put every feature in there. So I think we're just about done here. I think I work for the best company on the planet. We are trying to help people make sense of data. We do that through graphs. We do that through graph technology because the world is very connected. Our data is connected. We're connected. We're trying to help people understand the connections in their data and make use of it. Some of the things that we're very proud of is the International Consortium of Investigative Journalism. You guys might remember that from the Panama Papers or the Paradise Papers, trying to understand, potential financial misgiving or things that shouldn't be going on financial in the world. Also, NASA trying to help them understand the lessons learned through their databases in the past issues and how they can actually go to Mars faster, and then the curing cancer as well as Neo4j being used to help people map correlations between causes and cures as well. So a lot of things that we're doing to try to help people understand their data through graphs. As far as resources for you guys, there's a couple different resources. There's a sandbox, so you don't have to install anything. It's got you can spin up a sandbox online. It has preloaded data. There's also a lot of developer tools and a community as well. If you're looking for the code that we use for the correlations for the citation network, you can find that here. It's also in the Graph Algorithms book, but it's on the O'Reilly GitHub for this as well. So I think that's it. So thank you everybody again for your time. Find me later if you want to chat more about graphs in general, because I love that topic.